Hello everyone, welcome to the lecture 12 in the course Diffusion in Solids. So far we have talked about the continuum approach for diffusion. We looked at the flux from a macroscopic point of view, then we try to arrive the relation for different concentration profiles for different diffusion equations, and as such we have not worried about how the diffusion takes place. Okay, so we have not talked about the mechanisms of diffusion. Okay, what is happening inside. Now, in this week we will start, and in the next week also we will continue talking about the mechanisms of diffusion, how the atomic movement happens inside a solid. Now, to do that, first let us revisit some of the concepts about the structure and defects in crystalline solids, which will also be important to understand the diffusion behavior. Some we will use it in the next week. Some also will be important when we talk about diffusion in some specific class of materials. So, we will look at the basics of crystal structure, the voids and defects, and then vacancy concentration, how to determine it, the equilibrium vacancy concentration. So, you are aware that there are different types of bondings that exist in materials, in the solid materials, and that can be ionic, covalent, metallic, van der Waals, or hydrogen bonding. We as such in our course will be focused mostly on the metallic classes of materials, and although we will definitely talk also about ionic and the covalent bonding when we talk about the semiconductors, the silicon will come into picture, and so on. So, mostly the metallic bonding, metallic materials is what is our focus. Now, you know that solids primarily have a crystal structure, so to say, and of course, there are some solids like glass which are amorphous in nature, but majority of the metallic materials are found in to crystallize in a particular structure, and there are 7 crystal systems which are usually defined: cubic, hexagonal, tetragonal, and whenever you are defining a crystal system, what you read is two important relationships: how the lattice parameters are related to each other, and how are the angles are in each of the crystal systems. So, I am not going into very deep of everything because that is a separate subject in itself, but just to give you a brief overview so that we are prepared for the, and when we use this in our lectures on diffusion mechanisms, then you are already aware of them. So, for example, cubic is the structure with the highest symmetry, where you have A equal to B equal to C. So, here, and alpha is equal to beta is equal to 90 degree. So, all the angles are 90 and all the sides are equal. Hexagonal and tetragonal are what are the uniaxial materials, where you have two sides equal and one side is different. For example, in the hexagonal case, you have again the C axis, whereas you have A being equal. In the tetragonal case, you have also the base is a square base with A and A here, and C is the axis in the perpendicular direction. Although in the case of hexagonal, the difference is that although two angles are 90 degree, but the one of the angle is 120 degrees. Whereas in the case of tetragonal, all the angles alpha, beta and gamma are 90 degrees. Then there are other crystal structures, for example, rhombohedral or triagonal, where A is equal to B is equal to C. All the angles are equal, but that they are not equal to 90 degrees. Then you have orthorhombic, where all the angles are equal, but A is not equal to B is not equal to C. You have monoclinic, where the sides are not equal, two of the angles are 90 degree, third angle is different, and then you have a system with the least symmetry, where neither of the sides are equal, none of the angles are equal and are not equal to 90 degrees. So, an activity question for you: what is the difference between a crystal structure and a crystal system? So, crystal is basically lattice, that is where to repeat, and plus motif is what to repeat. So, for example, you have a unit cell of BCC, that means this is only lattice tells you the points. So, these are the corner and these are the body centered. Now, when you put actual motif, the atom so to say, or molecule it can be, and when you put it, then you generate a BCC crystal. Okay. So, this is a crystal and this is a lattice. So, crystal is when the motif is added to a lattice. So, these are some of the basic some of the main elements for which the crystal structure is given. Of course, there are several others you can try to find out, but you can see FCC, HCP. Luckily for us, most of the metals crystallize in simple cubic structures, but there are definitely metals or other elements which crystallize in different structures. For example, tin is tetragonal at room temperature, it is diamond cubic at less than 13.2. There are metals exhibiting allotropic transition from BCC to FCC. For example, iron is there. Then you have titanium which is BCC at greater than 882, and so on. Then for these 7 crystal systems, there are 14 Bravais lattices. You might have heard of the cubic Bravais lattice, which has a simple cubic unit cell, a body centered and a face centered. Similarly, for hexagonal, you have a primitive. This P basically is primitive, means only the corner atom or the number of atoms per unit cell is 1. So, you have hexagonal primitive unit cell. For tetragonal, you have primitive and the body centered tetragonal, which is, by the way, the crystal structure of martensite in steels. You have a rhombohedral primitive cell. Orthorhombic is the one where all the possible lattices exist, primitive, body centered, end centered and the face centered. Similarly, you have for monoclinic there are 2, triclinic there is 1. One more activity question for you. You see that why is there no face centered tetragonal lattice? So, of course, this is not in the scope really of this course to understand why there are only 14 Bravais lattices. Actually, if you see there are 4 types here. So, if there are 7 Bravais, 7 crystal systems, there should be ideally 28 Bravais lattices, but why are there only 14? Okay. So, that is also understood by people, but just for additional reading, I want you to find out why is there no FCC or face centered tetragonal lattice. The unit cell is the smallest portion of a crystal lattice, which when repeated in different directions generates the entire lattice. So, this is a typical cube unit cell. This is A, B, C, which are the unit cell parameters, and alpha, beta, gamma are the angles between these. So, this is how it is defined. Some of the features of the unit cell, it is often a point of interest to look at what is the relationship between the lattice unit cell parameters and the atomic radius, because that is different for different unit cells. For example, if you look at an FCC unit cell, for FCC unit cell along the phase diagonal. So, FCC is basically where you have a corner atoms and you have atoms at the phase center. So, if you look at any of these phase centers, these atoms are actually touching each other. So, you may recollect that this is how we draw it when we are drawing the unit cells, but in reality they are touching each other. So, if they are touching each other, then this is R, this is 2R and this is R. So, this 4R becomes equal to root 2A. Root 2A is nothing but this face diagonal length. So, therefore, for FCC A is equal to 2 root 2 R, which allows me also to calculate the atomic packing fraction. So, what is atomic packing fraction? Is volume occupied by the atoms divided by volume of the unit cell. Okay. So, volume occupied by the atoms is effective number of atoms into volume of individual atoms divided by volume of the unit cell. So, you see effective number of atoms in FCC is 4, which is each corner is shared with 8, each corner atom is shared among 8 unit cells. So, 8 into 1 by 8, there are 8 corner atoms, plus the face centered atoms are shared with 2 unit cells, gives you 4 effective number of atoms, multiplied by volume of individual atoms is 4 by 3 pi r cube, divided by volume of unit cell, which is A cube. And if you use this relation, A is equal to 2 root 2 R here, then you will end up in a packing fraction of 0.74. It is also sometimes important from a diffusion point of view, from a deformation point of view, to talk about the planar density. So, planar density is basically number of atoms on a given plane divided by area of the plane. For example, if I take a BCC unit cell, and if I talk about a 100 plane. So, this is a 100 plane, and in 100 plane, if you see that there are the atoms are shared like this. So, basically there are 4 atoms into 1 by 4. So, the effective number of atoms is 4 into 1 by 4 divided by the area of the plane, which is A square. So, the planar density becomes 1 by A square. Okay. So, you can see here, this is how we represent, we calculate the number of atoms. Similarly, if you want to calculate on 110, in 110 passes through the body centered atoms atom here. So, you will have the 4 corners sharing 1 by 4 plus 1 full body centered atom. So, 4 into 1 by 4 plus 1 divided by the area of this plane is, this is A and this is root 2 A. So, this comes out to be root 2 by A square. Now, similarly for 111, so 111 does not cross through the body centered, and this is how it can be drawn. So, it is 3 into 1 by 6 basically divided by root 3 by 4 A square. This is an equilateral triangle. So, the area is root 3 by 4 side square, and the side is root 2 A. So, root 3 by 4 into root 2 A whole square, this comes out to be 0.577 by A square. Now, when you have a unit cell, when you have atoms occupying the unit cell, of course, there will be empty space that would be left out, and those empty spaces are actually very important. These are called as voids in this cubic structures. Why is that important? Is because when we talk about the solid solutions alloying, the smaller atoms or the smaller alloying elements sit in those voids depending on the size of the void. So, for example, if we ask ourselves what is the largest spheres that can fit in the octahedral voids of FCC unit cell. So, you can have octahedral, you can have tetrahedral, depending on how the atoms are coordinated next to this void. So, remember, this is an FCC unit cell, where just to show, these are the face centered atoms, these are corner atoms, and this is actually the void. So, in the void, if another atom sits, what is the largest sphere that can fit in this octahedral void? So, the largest atom that can sit means that it will be touching these atoms. So, therefore, you can write R, this is basically the radius of the another foreign atom, plus 2R, which is the radius of the face centered atom. So, 2R plus R is equal to A. Okay, this is the distance between the two face centered atoms, where r is as I said radius of the regular atoms here, and small r is the radius of the interstitial atoms. So, therefore, now we know that root 2 a is equal to 4 r, that is for the FCC. So, therefore, a is equal to 2 root 2 r. Now, if you put a is equal to 2 root 2 r here, what you end up is the small r, which is the radius of interstitial atoms, is equal to root 2 minus 1 into r, or that is equal to 0.414 r. So, the interstitial atom, the largest interstitial atom that can fit in the octahedral void of FCC unit cell should be having a radius of 0.414 r. However, remember that it is still possible that a larger interstitial atom sits here, but then it will cause distortion in the lattice. Now, after looking at the structure, let us come to the defects in the crystalline solids. We have not still talked about the structure in ionic solids or in intermetallics, but that I will talk in the next part, in the next lecture. So, defects, when we classify ones. One is based on the dimensionality, that is the 0D effect, 1D effect, which are also known as line defects, 2D or surface defects, 3D or the volume defect, and 0D defects are known as the point defects. So, these are vacancies, interstitial, Frankel defect, Schottky defect. These are often the equilibrium defects. The most important line defects are edge and screw dislocations. Grain boundaries also play a very important role in diffusion, in mechanical properties of the material. Stacking faults, which is basically error in the sequence of the atoms arrangement. Then you have volume defects like dispersion, precipitates, inclusion, voids or cracks. Now, in today's lecture, we will only talk about the vacancies. Now, vacancies are considered as equilibrium defects. Why? We will try to answer this shortly. So, for example, if you take a pure element and only a mono vacancy being present, then this you can treat like a binary solid solution of A and B. Okay, like we treated A and B, we can treat pure element and a vacancy. So, vacancy we can consider like a B atom. Okay. So, if you do that, then also you assume that equilibrium number of vacancies is so small that we can neglect interaction between them, which means that at this point we also neglecting divacancies, which actually are present in the material, but we will see later that they are more dominant, especially at the higher temperatures. So, but for now, when we want to determine the equilibrium concentration of vacancies, we can restrict ourselves to the mono vacancies. So, how do we determine this equilibrium vacancy concentration? If we consider that the number of vacancies is very small, then the increase of enthalpy because of formation of vacancies can be written as delta H is equal to XV into delta HV, where XV is the mole fraction of vacancies, delta HV is the increase in enthalpy because of 1 mole of vacancy. So, see, vacancy means a bond has to be broken. A bond has to be broken means it will change the enthalpy. Remember, enthalpy is the total heat content of the system, which includes potential and kinetic energy. So, when you are removing an atom, you are actually changing the potential energy, which is the bond energies are changed. So, therefore, when you create a vacancy, there is enthalpy change that is involved. So, increase in enthalpy because of 1 mole of vacancies is written as delta HV, and if it is XV, then it is XV into delta HV. Now, when you change the vacancy, there will be also change in the pattern of vibration next to vacancies. The increase in thermal entropy because of this extra freedom of vibration can be written as delta S thermal is equal to XV into delta SV, and where delta SV is the increase in entropy because for 1 mole of vacancies. Now, as we said in the previous slide that we will consider A and V as binary solid solution of A and B. So, whenever a binary solid solution is forming, there is a increase in the configurational entropy of the system. So, the configurational entropy part can be written as basically delta S configuration as minus R x v ln x v plus 1 minus x v into ln 1 minus x v. So, the total entropy of mixing will be delta S v into x v minus R times x v ln x v plus 1 minus x v ln 1 minus x v. So, the total free energy after the creation of vacancies, initially let us say it was G A for a defect free A plus delta G. Now, this delta G is basically G A plus, so G can be written as G A plus delta H minus T delta S, and G A plus delta H v into x v minus T times delta S v x v minus R x v ln x v plus 1 minus x v into ln 1 minus x v. Now, this G, the x v can be called it as, we can call as equilibrium concentration when the G is minimum. So, that at minimum the delta G by delta x v will be equal to 0. Remember this from the mathematical concepts lecture, whenever the function attains a minima, the slope is 0 at that point. So, dou G by dou x v is equal to 0. So, now we differentiate this. So, the differentiation of G A is 0 with respect to x v. Here it is delta H v into x v. So, the differentiation will be simply delta H v minus T times. So, again here the differentiation is also delta S v minus R into x v ln x v, both are containing x v. So, we will apply the product rule. So, x v into 1 by x v plus ln x v plus again here also 1 minus x v in divided by minus of 1 minus x v, log differential is 1 by x, remember, minus ln 1 minus x v. So, this turns out to be delta H v minus T times delta S v minus R 1 plus ln x v minus 1 minus ln 1 minus x v. A little bit of rearrangement will give you this delta H v minus delta S v minus R ln x v minus ln 1 minus x v is equal to 0. Since x v is small, since the vacancy concentration we assume it to be small, 1 minus x v can almost be equal to assumed to be equal to 1. So, therefore, ln of 1 is 0. So, we can neglect this term. What it gives us is this, and therefore, R T ln x v can be written as minus delta H v minus T delta S v, and ln x v, therefore, we know that delta H minus T delta S is nothing but minus delta G v by R T here. So, the x v equilibrium, if you take exponential this side, can be written as exponential minus delta G v by R T. So, if you plot, if you represent this graphically, see this is how the delta H will vary, x v into delta H v, this is how minus T delta S will vary, and the combination of these two gives you the overall free energy, which will have a minima at x v equilibrium. Okay. So, beyond this, then the free energy starts to increase. Therefore, the vacancies are said to be the equilibrium defects, because you see that as you increase the x v, the free energy of the system is going down. So, system the thermodynamically it is favorable to create certain amount of vacancies because it lowers the total free energy of the system. And vacancy concentration, as we have seen, it depends upon the temperature. It has this kind of a relation. So, it increases and it becomes saturated after a certain temperature. In fact, there is an approximate number for at the melting point how much is the vacancy fraction. It is almost equal to 10 power minus 4 for most of the metals. So, we will continue our discussion on the structure and defects in solids in the next lecture also, where we look at some more type of defects and also look a couple of example in other crystal systems or rather other class of materials as well, not just the metallic one. So, thank you.